finished. It's here, so I explained that symmetries and topologies in combination give a rich variety of critical types of critical behavior, also in two-dimensional systems, and we focus on 2D, namely on realization of this in graphene with different types of disorder. And as I was talking about, was the situation where so the symmetry, which is called here lambda z, it just means that the corresponding component of the isospin is conserved. In physical terms, just means that two values are decoupled. So the disorder does not mix the two values, so you can consider just one species of Dirac fermions separately from the other. And then there are still several possibilities depending on what type of disorder you have. You may have a random potential, random vector potential, and random mass, a combination of them. And so depending on this you get different theories. And I focused on two situations. Maybe one, there is a sort of most generic type of disorder within one valley, and this corresponds to class A, which is a class of the quantum Hall effect, with a topological term, with an example is a coefficient theta equal pi that puts the system into the critical point of the quantum Hall transition without any negative. So, Dirac fermions in the graphene class, such type of disorder that doesn't make valid, gives the criticality of the quantum Hall, critical point of the quantum Hall type, and so with the conductivity that is critical conductivity of the quantum Hall transition, which is quite similar to what's in an experiment, but still somewhat small and numerical enough. So if it would be unity here, it would be close to what we see in experiment, but qualitatively it's pretty much similar. Anyway, I'm not claiming that. Because of course type of disorder in experiment may depend on preparation of sample and other details, at least on theory level. This, and a second important example goes when we have only random scalar potential. And so it's one species of Dirac fermion with random scalar potential. And then this is a symplectic class because there is a pseudo spin associated with sublattice. And again, there is a topological term. So there's a calculation here, a topological term. Here, so all this, in all these cases, when it's just when values are decoupled, you get some terms of the topological type. And it's again what is on the level of sigma model responsible for preventing this system from localization. And indeed, numerics shows that conductivity in this model just is metallic, and it's super metallic in the sense that it flows to logarithmically to infinity because it's symplectic class. Once the conductivity is big, then we know from the derivative calculation that it should become still bigger. It's logarithmic, and it flows to that's what we call super metal. It's infinite conductivity. And yeah, so the two groups that model the same time and obtain the same results. So schematically, what the scene can be presented as a following kind of beta function for this symplectic class. So if you don't have, if it's a non-topological situation, it's just symplectic class in PD, we know there is a phase transition here, there is a metal insulated transition in this symplectic class in 2 dimensions. So if the conductivity is sufficiently big, then you flow it's super metal. If it's smaller than some value 1.4, you flow to an insulator. So what happens here with this topology that you always I mean, one should just consider this schematically. It's not that the beta function here is sort of uniquely defined, but schematically, what happens is that you always, with this topological term, you always flow to a certain situation. So similarly, the quantum Hall effect, the topological term prevents you from localization.
So for the topological terms, are they always second order in Q? And you write down what the combination that respects the symmetry?
Oh, explicitly, yeah. So because Z2 topological term, it's in fact difficult question how to write it explicitly. Yeah. So you know that there is a topology, there is a mapping, and there is a homotopy group which is equal to Z2, and so all mappings from the sphere to the sigma model manifold can be classified according to this group. However, to write it explicitly in terms of sort of local expression is in general not possible for this.
Question? So how do you calculate the beta function in that case?
No, well, it's not, once again, that's what I say. You cannot really, so this part, it's always implausible. Whenever you see some beta function shown in the regime of strong coupling, in the majority of cases, with some rare exceptions, you cannot really calculate it. It's basically a schematic plot that shows you what happens. Yeah, that's the same as I already warned you about the flow diagram of the quantum Hall effect. That's the same story. There is no calculation. That's only a qualitative picture that shows what happens in this regime.
But even for large G, how do you...
No, for large G we know, of course. So here is, of course, that's a perturbative calculation. For large G, everything is under control, so you can calculate controllably perturbative effects. And if you have some topological, then you have topological effects which are here exponentially small, and they give you a feeling what they may do here. However, really the calculation here is, if you ask me why this beta function doesn't cross this, I don't know, 5 times, it's nobody. It's a minimal way of connecting it to localization, and that's what indeed seen numerically. However, there is no real calculation that will show it, and I don't think it exists in principle.
So in large G, you basically neglect the topological.
Oh, in large G, of course, the topological term is exponential. Large G, you have expansion, perturbative expansion 1 over G, and the topological term gives you effects which are exponential minus G.
Yes.
So, but of course, in this part, everything is in the same order, and so you just see that the topological term sort of works in the right direction, but it's not that you can really hope.
So in Trigger mentioned also the beta function will be positive. So what's super about the super metal? What's the experimental manifestation?
Oh, the conductivity is infinite. In 3D, you will flow to finite conductivity.
Right.
And here you flow to infinite conductivity. So in 3D, of course, you also flow to the infinite conductance, but the conductivity will be finite, right? It will be just a normal metal with metal. So here you flow in 2D, conductance and conductivity is the same. So you flow to infinite conductivity. I mean, it's just a word. Yeah. If you don't like it, it's confusing. It's a metal with infinite, the fixed point conductivity. Okay, so let me show you some very recent numerics we did with this, because I think it shows very nicely how all these classes manifest themselves. This is a modeling of graphene with rarer scatterers, rarer strong scatterers, in this way. And the way it's modeled, it's a combination of analytics and numerics. So first, it's not directly a tight binding model that's modeled. However, it's first reduced so that the scattering on each scatterer is calculated with T-matrix. This is done analytically, and then you map the program on a model, on a Hamiltonian, effective Hamiltonian of the size which is equal to the number of scatterers. So how you propagate between the scatterers, you know the scattering matrix of each scatterer. However, the positions of scatterers are random, and so you get to a random matrix, but it's of the size, not of the number of the latest size, but rather the number of scatterers. Yeah, that's what we call unfolded scattering theory. But anyway, and then this is put on computer. And this is a very efficient way to do it numerically for this type of scatterers, which are really rare and isolated. And so now there are 2 different types of scatterers. Impurities considered the first that we call scalar impurities, which do not mix Bayes. So they're short range, however, short compared to the distance between them, however, there's sufficiently long range, so finite range, and the range is such that you can neglect intervening scheduling. So we just by hand we put a scheduling matrix that doesn't expand. And another that we call addendums, these are sort of really sharp and they do expand. And in each of the cases, the strength of scatter is characterized by the scattering length. So which is here we call LS for scalar and LA for this addendums. Okay, yeah, so this is a conductivity as a function of length, and what you see here is that the conductivity increases when there is no value mixing, and that's exactly what I showed you before. This is this super metal. And in fact, there are two situations here, finite scattering length and infinite scattering length. And when there is infinite scattering length, it turns out that there are more asymmetries. It's just because the infinite potential preserves some particle symmetry, chiral symmetry, because it doesn't matter whether it's plus infinite. When scattering length is infinite, you don't know if it's plus or infinite or minus something. And so there are two different symmetry classes, but it turns out that the behavior is extremely similar in both situations, so one can distinguish them, but it's qualitatively very similar. Situation is richer when you have this addendums, because then when you have finite scattering length, this is just the system problem is a normal class, which is A1. This is a class that you normally have in a system with random potential. And there should be localization. And indeed, this is what we see. So these are curves for different strengths of impurities. When impurities are weak, they simply do not reach the localization. So these curves also will go to localization, but we simply do not reach it. But if the impurities are sufficiently strong, they start to see localization. It's a nice localization. And now we make impurities still stronger. And you could think, okay, localization should become more efficient, but it's not the case. This goes again up and tends to essentially to a constant. And this is because when the impurity are infinitely strong, this is a chiral symmetry class, and in the chiral symmetry class there is no weak localization to any order. So if you look at the conductivity as a function of the impurity strength, certain system size, it first goes down because of localization, and then when you increase impurity strength further, it returns back because you go to the chiral symmetry class. So for strong, very strong but finite impurities, we first see the behavior of this chiral class, the constant conductivity, and then there is a crossover to this normal orthogonal class. They start to see localization. So you see 4 different symmetry classes here, and it makes the problem even still richer when you now include magnetic field. So now let's switch on to magnetic field. And again, there are 2 situations of scalar impurities and of this addendums. So let's look at scalar impurities. And with scalar impurities, we consider 2 types of situations when this scalar impurities are symmetrically and asymmetrically. And the strength is sort of plus minus, and but all have the same sign. So when it's symmetric, then what we see that we flow into some finite value of the conductivity, and it's also shown here, this finite value. So these are not error bars, that's maybe not a bit unfortunate. These are mesoscopic fluctuations that are shown here. So error bars for average conductivity are in fact very small. So it's just these red points, and this saturated some value, which is now slightly larger than this 1 over pi, and that was the value on the previous plot, and that's exactly the value. So what we see here is that the system flows into the one-hole fixed point, as it should be. Yeah, we know that when we are at 0 at the Dirac point, with symmetric disorder in magnetic fields, there will be a center of the Landau level, exactly sitting at this Dirac point, and so the system flows into the critical point of the one-hole field. So this is a part of this Proustian sigma model flow diagram.
So what kind of model? So what model is this?
So the model is graphene with rarer scatters. which are characterized by some scattering length. And here, the scatterers do not mix values. So we characterize scatterers by scatter matrix. And there are two situations. One, they completely sort of scatter between values. In another case, they scatter only within each value. So
And the time versus symmetry breaking comes from
magnetic field.
What's the reference to this?
What is?
The reference to these plots.
Oh, reference.
Yes.
You mean, but so the reference. So this is from some very recent kind of by a number of authors, including Crossroad, people plus Mishtikov and Ostrovsky. Oh, and then plus two students. Yeah, so here you see the flow into the quantum Hall critical point. Now, at the moment, the impurities, and this happens also for finite strength continuous. At the moment, the impurities are not symmetrically distributed, there is an average value of the potential, and it shifts the system away from the center of the Landau level, which means from the quantum Hall critical point. And therefore, we start to observe localization here in the situation. So even when values are, although values are not mixed, and before it was always critical. However, with magnetic field, in the moment we shifted from the center of the Landau level, from the quantum Hall critical point, we get localization. And that's what we see. From the sigma model point of view, it means that the topological term now has a theta coefficient which is not equal to pi anymore. By magnetic field, we tune the strength of the theta term. That's the value of the theta angle. And therefore, we get localization. Because we are now, because we have magnetic field, and in addition, we are away from the Dirac point due to, essentially, due to potential of impurities. Okay, and in the case of mixed values, we see the same localization, and it's because here, because values are, even when disorder is symmetric, yeah, so on the plot, so the two curves here, in one case we flow into the quantum Hall critical point, and in another case we flow into this zero conductivity critical point. So what happens when values are mixed? So now the Landau levels, because of splitting, because of inter-value scattering, the Landau level, the critical point, critical energy splits in two. And therefore, even when there is a symmetric distribution of impurity, we see it exactly at the Dirac point, but the Landau level now is split. The critical value, or the critical energy splits in two, and we are now in between. And therefore, we flow into the zero conductivity fixed point, and so we see localization. That's what we observe here. And if we look at the details, then it turns out that there are some crossovers depending on the relative strengths of impurities and the magnetic field. Eventually, they are always in this class A of the quantum Hall effect, but in between there are some complex crossovers, and we can, because of these crossovers, we can see here where non-trivial behavior, for example, here it goes up, then it goes down, and then it even goes up, and this is explained by crossovers that we see here. Yes, Leo?
I was just going to ask, yeah, I mean, maybe that answers, but I don't quite understand why there are all these crossovers. So when you're turning on intervalley scattering, so what, from the point of sigma model, what did you?
So now there are crossovers both in this case and in this case. Yeah. So now these crossovers are, so now I'm not sure which in which.
Let's say you're symmetric disorder and you're in a magnetic field, but with or without intervalley scattering.
Okay, so say without intervalley scattering. So we have strong impurities. So in the limit of infinitely strong impurities, this is this class D3, which takes into account that there is this particle Hall symmetry.
Right.
So then there are two things happening. One is that there is a magnetic field, and the other one that impurity have finite strengths. Depending on which one happens first, if first system feels that impurity have finite strengths, you get to the class A2, and if you first feel the magnetic field, you get to the chiral class A3. But eventually you feel both of these things, and you end up in the class A, which is sort of the least symmetric class. So you break two symmetries, and the question, depending on which one you break first, means which parameter is larger. You will go through this class or through this class.
Well,
If they are all the same order, there will be no.
Sorry, but which of these is what's, you know, you get intervals.
So you start from this D3. This is when you go up.
That's no intervalley scattering, right?
Yeah. That's
high
here.
level.
Here there is no intervallic scattering at all. You start from D3, and this is super metal. That's anti-localization. You go up. Eventually, you end up with a finite value which corresponds to the quantum hole. And now in between, there may be one of these two classes.
Oh,
But one should more carefully look what happens here in between. Yeah, and similar stories here. You start from chiral class BD1 and then we end up in class A again, and depending on whether magnetic field or finite impurity strengths are more important, you have some intermediate sequence. Yeah. There was
Sorry, the same question.
oh,
Yes. Did you look, for example, at sigma xy? Because when you're approaching that critical point, it looks like sigma xy would remain constant, right?
this one.
Right.
That's more or less this range.
Oh, okay, that's sigma xy.
That's no, sigma x. Oh, sigma xy. Yes. No. This is longitudinal conductivity. That's a value of longitudinal. So we sit as a direct point. Yeah. So when you sit as a direct point, there will be no sigma xy. Yeah? So when you are exactly at the critical point, at criticality, in the middle, at direct point, in the middle of zero sum now level, yeah, there is no sigma xy. What sign will have sigma xy? So here there is no sigma xy.
But from Pushkin's diagram, it looks like it's half.
Oh yeah, that's a good question. That's a good question. Yeah. So from Pushkin diagram, in Pushkin diagram, this point corresponds to sigma xy equal to pi, right? So because in Pushkin diagram, in Pushkin's theory, sigma xy and theta angle is the same. And here, sigma x theta angle is sigma xy plus pi, and this pi comes from the anomaly and that you can understand already from the previous calculation without any magnetic field. So without any magnetic field, we get here this Pushkin term, well, this topological term with pi, although sigma xy is obviously zero because there is no magnetic field at all. So there is a pi contribution to the topological term to the theta angle, which is not related to sigma xy, but it's, yeah.
I think that pi is coming from the fact that a single Dirac cone has very phase pi.
Yes, that's all, yeah, if it explains, yeah, that's the same, it's of course, it's the topological properties of Dirac fermions, and it's related to Berry phase pi to chiral anomaly, and so everybody may understand this in a way he or she likes it. Right, that's all it's connected.
So the story where the symmetry class changes with energy scale, should I think of it as, originally I'm pretending my Q matrix sigma model is restricted to a certain manifold, but actually it can wander away from that manifold because there are some symmetry breaking.
Yes, of course, yeah. That's of course usual story that depending on scale on which you may have small symmetry breaking perturbations, and then on short scales, spatial scales, or sufficiently high temperature, you are in some symmetry with very small effects due to symmetry breaking, but eventually the symmetry breaking terms are always relevant, and they restrict then your Q field eventually to some other manifold. So some degrees of freedom get sort of frozen, and so this is what are all these crossovers from the point of view of field theory. Okay, good.
But is there any cases where it goes the other way, where it becomes more symmetrical?
Where it becomes more symmetric.
I understand this simplest easy plane.
Yeah, that's a good question, and in principle, that's not excluded. Yeah. So under RG, some symmetry may emerge. That's certainly correct, but let's see, it's not that it will be the symmetry that it flows, at least I'm not aware of any example that it would flow to a symmetry class in this sense, which has more symmetries than the original one. So we know some different types of symmetries, like when sigma models flow in Versumino types fixed points, which have more symmetries, and so this types, but not well. So there was a proposal by Martin Zimbauer that the quantum Hall critical point fixed point is described by some kind of Versumino theory, which would mean that that it's in certain sense more. I don't want to go into detail. So this Versumino theory is more characteristic for chiral classes. So in certain sense, it would mean that the theories became similar to the sort of chiral class theories, but I don't think there is any.
Let me ask you a simple question. So like that.
So,
yeah. So in the cases that's more that you have here, for example, it's more common where you reduce symmetry. So let's say you go from D3 to D2. So is it if I could visualize this manifold, is it analogous to, let's say I have, if I have some easy plane isotropy in there, some
right, yeah, sure.
I go to some subspace of the S2,
yes,
then
yes,
circle on the equation.
yes.
So the people who can visualize these manifolds can really visualize A2 as some subspace of D3?
Yes, yes, of course. Yeah, it just means that some of your massless modes became massive. Yeah, that's
Can you visualize all of them?
I mean, these are supersymmetric spacing. Okay, so if you think in terms of yeah, it's more or less like if you start from the group SU2 and then you reduce, that's more or less what happens in this D3 to A crossover, yeah? If you start from the group SU2 and then you end up with a sphere. So that's I think the simplest example. Yeah. And so in D3, that's a group, you have a Versumino term there, and then when you reduce it to a sphere, so this Versumino term gives rise to a topological term on this sphere. Yeah, that's I think a really simple example of such. But once again, in principle, with a supersymmetric manifold, but the normal, some part of it is of this sort. Good. So just comments. I don't want to go into details of topological insulators. First of all, I don't have time. Second, I think everybody here works on topological insulators, or at least every second of you, and so probably you can tell more than I. So let me just say a few words just to connect what we discussed with topological insulators, and we'll go to interaction. So now it's only about integer topological insulators. So well, there have been. Well, I don't want introduction. Will be very, very brief. So just at least some subset of people who contributed. There are many more. So including Victor, where he just came. So the quantum Hall effect is, one example of a z-topological insulator, because you may have states that are classified by topological states, classified by integer, which physically has the meaning of the number of H states, and another class are the z-topological insulators, where we have either 0 or 1. H state, and the experimentally observed examples correspond to the class E2, so this is a symplectic class in 2 dimensions and 3 dimensions. I mean, experimentally observed, one should be careful in what exactly is observed and how convincing it is, and so, but at least to we know that the system should be there, and there are at least experimental indications that this topological behavior to a certain extent is seen. So, from the point of view of the sigma model, the classification goes like this. It basically generalizes what I told you before. So in fact, there were two types of sigma models. Some topologies here of the type Z and of the type Z2. And basically the classification is based on possibilities to include, to have such topological terms in sigma models. And so this is based on work by Anders Ludwig and co-workers who just generalize this ideas. So basically, to detect the existence of topological insulator of certain symmetry class and certain dimensionality, one should analyze the homotopy group of the sigma model manifold, and which will tell you whether you can add, whether there may be a topological term that would protect the system from localization. As we have seen, these are the topological terms that protect from localization, and the topological insulator of the type Z means that the homotopy group pi d of this manifold is Z, and then the term that would protect is the Bezzomino term, and this is, for example, the term that protects H states from the point of view of the sigma model, H states of the quantum Hall effect, and the existence of this term on the boundary corresponds to the existence of the topological term in the quantum Hall in the bulk. Zeta term in the bulk corresponds to the Bezzomino term on the boundary in the topological insulators. And if the relevant homotopy group is Z2, then you can add the corresponding Z2 topological term, and therefore you may have a topological insulator. So the Z2 topological term is explained in the boundaries 0 or pi, and so the pi topological term. And that's exactly what emerged in graphene, in one-value graphene with random potential. This is what will protect the system from localization. So this term makes boundary situations non-localizable, and topological insulating d-dimension just means that d-1 dimensional states may be made non-localizable. As an example, so this situation corresponded to 2 dimensions. That was graphene, one-wave graphene with random potential, and where topological term, Z2 topological term may exist, just without any calculation it may exist because of homotopy group. So that's an example for when it appears, but the fact that it may exist follows from the homotopy group. And therefore, there is a 3-dimensional topological insulator in the symmetry class. Because in 2D you can protect states from localization, and now all these homotopy groups are known, and this yields this famous table of topological insulators. So this is the dimensionality. These are symmetry classes of Hamiltonians. So these are symmetry classes of the compact part of the sigma model. Yeah, so for this homotopy group, only compact sub-manifold of the sigma model manifold is important. So you should look on the compact part. And if you just look at the corresponding homotopy groups, then you get this table. And so, for example, in 2-dimension, so this Z corresponds to class A in 2-dimension. This is the quantum Hall effect. So this Z2 corresponds to class A2 in 3-dimension. These are the usual topological insulators, and so forth. So there is a direct way to understand this based on this disorder analysis, and quite remarkably, it agrees fully with the result obtained by Kitaev before by looking at just clean systems and using this analyzing topology in the space of Bloch Newtonians. So the result turn out to be the same over the closure symphony, quite different there. So at this point I want to stop with symmetries topology block and come to interactions. Let's see what I can tell you, but at least I will give you some flavor of what can be done with interaction. So what are, in general, effects of electron-electron interaction on these disordered systems? And we're sort of on a, before going to again to criticality, we will first briefly discuss effects of electron-electron interaction on just on a metallic regime, on the level of corrections, and then we will see what it means for critical constant. So there are two different types of effects. So one we call renormalization, and the one we call dephasing. So physically there are two different types of processes. So renormalization are virtual processes with energy transfers which are larger than temperature, and these effects become stronger. This may become stronger when temperature is lowered, just because they're determined by energy's high temperature. And in low dimensionality, they are typically singular in limit of zero temperature. And so therefore, it's very important to include them. And they belong to the same sort of class of phenomena. I mean, in the sense that the renormalization phenomena, like ferrolipid renormalization or Kondo latitude-lipid effect, power loss, Fermi singularity. So these are all phenomena coming from sort of virtual processes with high energy transfers. And then there are processes related to real inelastic scattering, which are determined by energy transfer smaller than temperature, and they of course become thicker when temperature is lower and then vanish in zero temperature. And they're all so on the level of renormalization group, so this will be included in RG, whereas this will essentially determine where we stop the RG. Okay, so let's start from interaction corrections due to renormalization. One can, so basically, in the first order interaction, one can draw a number of diagrams. So what is shown here is a bubble, just a conductivity bubble, with one interaction line inserted, and it's then it's addressed in all possible ways by the letters, by diffusion letters, and these plus minuses are signs of the energy, and or frequency, or whether it's retarded by advancing Green's function, and depending on this, and all of them should be included, and so depending on the signs, because the letter is always between plus and minus, and so retarded and advanced, and so there is a set of such diagrams, and they correspond, these are exchange diagrams, and there is a corresponding set of Hartree diagrams. So this was first worked out by Shura and Aronov in famous papers in 79, and so Shura and Aronov diagrams actually first 5 of these diagrams, and they are dominant at low temperature. This all then later been extended also to high temperatures, to so-called ballistic regime, and temperature is above an inverse scattering rate, and then I should also include a few more diagrams, so I just copied this from my papers.
So in the ballistic regime, should one still use a sigma model, or should one go back to sort of electron Green's function diagrammatic perturbation theory?
That's a perturbative calculation. For this sigma model is not one needed, and so we did this calculation, and ballistic regime in magnetic field So that was,
Even in
use the
principle-
sigma model, however one may do it, but then one should use the ballistic sigma model because one wants to use the scales which are shorter than the mean-free path, so one should, it's beyond the diffusive.
I thought the elementary building blocks of the sigma model were the diffusons.
Right, but one can generalize it to make it work also in the ballistic regime. However, it's not needed for this help. So basically, what I'm saying that when you go into the ballistic regime, the high temperature, then the diffusons and couperons will not have this universal form as they have. However, they will depend on a specific type of scattering. Still, you may have calculated ladders. You can calculate the ladder also in the ballistic regime, but then we should specify what exactly impurity is scattering. So the results will depend on whether you have isotropic scattering or small angle scattering. Okay, I don't want to go into details of this ballistic regime, so let me just say a few words about this diffusive calculation. So this is a typical diagram of this in the diffusive regime, and it looks quite simple. It's just one interaction line inserted in a bubble of conductivity and pressed by impurity layers. Yeah. And so the calculation of this diagram proceeds in a very similar way to how we calculate quick localization. There are two diffusons here. There is one interaction. There's two diffusons. There is one interaction line, and there is 1, 2, 3, 4 Green's function. And again, we separate slow and fast degrees of freedom. So we neglect this Q. So P are fast, and Q is slow. Low temperature, and so you can neglect this Q here, and therefore the two integrals of again Q just split. The result is shown here, and in particular, if you take short-range interactions, basically a constant interaction, then the result looks very much similar to the big localization correction. It's again one integral of dq over dq squared. And this resulted from the fact there were two diffusons now, but there was also additional energy integration because it's now inelastic. And so if you integrate by energy, it's interaction, and once you do it, you again get. So in 2D, you again get logarithmic behavior very much similar to the quick localization, except that the cutoff of the logarithm may be different. So here is calculated at frequency scale, and then the cutoff is just frequency, like also before big localization. Now, if you do it finite temperature, then the cutoff of the logarithm is temperature. And now this makes a difference with the big localization, where the cutoff would be not temperature, but the dephasing time. But otherwise, it's very similar. And the coefficient here for Coulomb interaction is just some number of order of unity. So again, similar to big localization. So that was an exchange diagram. If you include corresponding Hartree diagram, there will be a similar contribution from Hartree, but the coefficient will depend on strength of the interaction. So in general, it depends on the Fermi liquid constant. Question?
So what's the dephasing time?
Here there is no dephasing. Yeah, that's
But what's dephasing before? I guess I forgot.
what is dephasing time?
Yeah.
So dephasing time is just inelastic relaxation time. Essentially, it's a lifetime of electron determined by
a single particle momentum. It's 1 over tau that appears in the single.
no, 1 over tau that appears is elastic time. That's impurity scattering time, and there is this time is just it's a short time, and it serves as an ultraviolet scale for this diffusive theory. So the theory
Right. So
is
what
all times longer than the impurity scattering time.
So you
Now the
don't-
dephasing time is an inelastic scattering time. At low temperatures it will be longer, and it serves as an infrared. So it stops.
Yeah, but it's not you don't put it in the theory. Like when we were doing just
No,
Just
you
so I
should
know.
calculate it separate. So basically, so here it doesn't appear at all. So this is cut off this by temperature. For weak localization, you basically it's what will cut off the theory. You calculate weak localization.
Conceptually, I understand it. Sometimes you like put on the magnetic field or put on thermal effect or interaction, you will cut it off. But you say you calculate in some other framework? Or?
No, you can also so when you write a sigma model, it knows everything, including, of course, this the inelastic time. Yeah. So.
But in the last time you need to interact.
So, but when you do the RG, for example, it will not enter there explicitly, because these effects are not of RG type. Yeah. They are. However, they will tell you where to stop this RG. Yeah? This is not logarithmic effects. They will in 2 dimensions. You will not see them in RG. However, they tell you where the RG should be stopped. It's.
But you need interaction for that.
Yes. No, of course it will be an interacting. Yeah. So in a moment it will be interacting sigma model. Yeah. So and then, but before sigma model, you can say if you do everything just perturbatively. Yeah. You calculate. There are 2 types of corrections. So one is a weak localization correction to resistivity, and this you should cut off by dephasing. Okay. That you should calculate, and I will show you in a moment how you calculate it. And another type of correction is due to this interaction used to renormalization. This is what's shown here, and this is directly cut off by temperature. So it doesn't.
And these 2 effects add? Or
they add. Yeah, they just add. Yeah, they just add. Yeah, I will again show this formula. And yeah, that's what I was thinking.
If the Kurog interaction is Creed Kurog interaction?
So, okay. So that was a result for short-range interaction. Then there is just the interaction strength. Yeah, U of 0, U as a momentum 0. If U of 0 is constant, just number, yeah, you get it as a prefect. Yeah. Now, if you have a Coulomb interaction, then U of 0 will be infinite. Yeah. But then, of course, you should take into account screening as usual. But it's screening by the system itself. Yeah. And it's a non-trivial screen, it's a dynamical screen because it's all at finite frequency. So when you work it out, you get here the universal number, as often happens for Coulomb interaction. Yeah, that's, okay, good. So you see that there is a correction due to this interaction, which scales as logarithm in 2D and as a power law t to the temperature to the power d over 2 minus 1. In other dimensionalities, so below in 2D and below 2D it's singular, it diverges in the limit of 0 to temperature. The overall factor is sum of the exchange and Hartree. So this constant f is negative. It's just definition of this fertility constant. So these 2 terms have opposite signs. Yeah, as we always expect from exchange and Hartree. And the sign is such that exchange wants to sort of localize the, and Hartree wants to delocalize. Yeah? So exchange suppresses conductivity and Hartree enhances conductivity. Yeah? So if the interaction is relatively big, then of course exchange will win, and you will just get additional localizing correction. However, if interaction is sufficiently strong, then this term may be stronger than this one, and it may force the system to flow into metal, whereas it was flowing, say, in 2 dimensions, whereas it was flowing in the insulator without interaction. And this is basically in the core of this explanation of the theory of metal insulator transition, Finkelstein. So the reason is just the fact that this correction may change sign due to sufficiently strong interaction, and it's already false from it's actually one of speculative calculation, but of course, to see what happens then, one need to have the whole RG, and this is what was done by Finkelstein. Okay. Yeah, so there is something about ballistic regime. I skip this. Yeah, so how does one see it in experiment? So as I say, this is a logarithm in 2D. It's a logarithmic dependence on temperature. However, big localization is also logarithmic to temperature. So in principle, they will add, and one should try to disentangle them. So one way to see them separately, and namely to see interaction correction, only is to look at the magnetic resistance. So in strong magnetic field, relatively strong magnetic field, the weak localization is completely killed, as we know. But the interaction correction persists because it's based on diffusion, not on Cooperon. There was no Cooperons here. Right? So these letters with diffusion letters. Yeah? So magnetic field doesn't make any harm. Moreover, if you calculate, it turns out that the correction doesn't to conductivity doesn't depend on magnetic field, and as a result, correction to resistivity becomes p squared in magnetic field. So you can very nicely see there is a logarithmic correction to resistivity, which has a dependence expected. The expected to be correction to resistivity, which has a p squared dependence on magnetic field, and temperature dependence, which is log T at low temperature. In the diffusive regime and in the ballistic regime, it's one of the behavior. This is what we calculated relatively recently, and this is an example of such an experiment. So you see this parabolic type of magnetic resistance, which goes linearly with p squared, so it's parabolic. And if you look at the temperature dependence, so this is this curve, this is a function of temperature, and at this range, it's logarithmic, and at high temperature, it becomes this one, this ballistic behavior. So the diffusive behavior is this low temperature behavior, and this log T behavior due to essentially a lot of interaction correction. Yeah, so that's a correction to the conductivity. There is a related effect, which is correction to the density of states. Now, when I say density of states, in interacting case, one should specify which density of states. So, without interaction, it's the density of states is unique. With interaction, there is a thermodynamic density of states, which is just dn over d mu, essentially. And there is a single particle density of states, which is just imaginary part of the single particle Green functions. For non-interacting case, they are identically the same. For interaction case, they behave essentially different. So dn over d mu remains uncritical. There is nothing interesting happens with it. Whereas the single particle or tunneling density of states, which one measures when one just tunnels in the system, becomes very non-trivial. And one sees this on the perturbative calculation. So it's a similar type of physics. Oh, actually, maybe I should comment what actually this interaction correction, what is the physics of this? I think I should just short comment. So I think it's easy to understand, especially if one looks at the corresponding Hartree diagram. So the Hartree diagram corresponding to this one would be. And then the physics is quite transparent. So these are just impurity lines. So think about this as there is one impurity, sigma, which line is just impurity. And now the electron propagates, and it's scattered by impurities. But these impurities also create some density inhomogeneity. And with density inhomogeneity also scatters electrons through the interaction. So there's a coherent scattering of electron on a set of impurities, and on density and homogeneity, which is produced by the same set of impurities. And that's essentially meaning of this. So interaction, in a certain sense, renormalizes the disorder by producing this density scattering on this homogeneous density. Yeah.
So I guess for every disorder realization, you would have a inhomogeneous density, right?
Right.
And this is why in the end this Hartree diagram is finite, right? Because there is a finite just electrostatic full of energy cost for having a finite.
I'm not sure what's the question.
No, I'm just commenting, and the question is coming.
Okay.
So that way, I understand why this Hartree part does not like localization, right? Because it's just essentially electrostatic energy cost of having.
Oh, yeah. Okay. No. So here I'm not sure. So it's a simple. Okay, maybe. Yeah. I don't know. So I don't have so intuitive explanation why it's delocalizing. But
right. And the question actually was about the exchange. So how to understand what the exchange is trying to do a localization.
Yeah, so exchange. Yeah, one thing I don't have a simple explanation why it should be localizing exchange and how to be localizing. And that's I'm not sure I can explain in simple words. Yeah, I think we had a question.
Yeah. it's like if I look at this diagram, and you have this interaction corrections, which part of it is, which part of this diagram is important, which one is not? Like, for example,
Which part is what?
well, is the vertex correction crucial? This sort of,
This one?
yeah.
Oh, of course, yeah. That's a diffuse one. That's where the whole everything comes out. It's so the whole behavior comes from the fact that you have this
I see. So
infrared singular propagators.
no, but you have a diffusion in a wiggly line, right? That's a diffusion as well.
I mean, the fact that you have this non-trivial low temperature behavior, the diagram exists also in ballistic regime I explained. In ballistic regime, it would be just one impurity. In the high temperature regime, you can just keep here essentially one line and calculate it, and you will get a contribution.
I guess what I'm asking, for the wiggly line,
Wiggly line, that's interaction.
oh, it's not a diffusion.
Oh, no, sorry. This is interaction, and diffusons are this
Okay.
sorry, yeah. This is interaction line, and this is diffusons.
Okay, I just confused notation because before.
Yeah, sure. Yeah, maybe I used, sorry, maybe. Yeah, so now this is interaction, and this is a diffusons line. And diffusons make this infrared, produce this non-trivial infrared behavior. It just means that this thing goes for a long distance in space. That's a coherent scattering on many impurities within up to the scale which is set by temperature. Many impurities plus density and homogeneity is created by this many impurities. Good. So tunnel and density of states. Yeah. There is a similar diagram, again exchange in Hartree and similar calculation. And for short-range interaction, the result is more or less the same. So the correction to the tunnel and density of states for short-range interaction is the relative correction to the tunnel and density of states is of the same type as the relative correction to the conductivity. So it's not very surprising. So the only thing that one should emphasize here is that there is a correction. Yeah, that so without localization, I told you that there was no other parameter and in the theory and tunnel and density of states. Well, density of states was uncritical. That was just unchanged by localization effects. Yeah. So with interaction, there is a correction. The short-range interaction is logarithmic in 2D. Moreover, if you take Coulomb interaction, and namely the exchange correction, it turns out that it's not logarithmic in 2D, it's even log squared in 2D. So, and this, yeah, okay, so this comes in the calculation from the regime of, from the interaction range of small momentum. So for conductivity correction, everything is determined by momentum such that dq squared is of the order of omega. It's typical for diffusion. So for this tunnel and density of states, it turns out that dominant contribution comes from the range where dq squared is much smaller than the omega, and this gives this log squared. Yeah. So the reason, yeah, one can trace back this big, yeah, so effect is much bigger. Yeah? Moreover, it turns out that there is a range of parameters where the correction to conductivity is still small, but this correction is not small anymore because it's log squared. And what happens in this regime that this log squared gets exponentiated. So the tunnel and density of states is exponential minus log squared suppressed. And one can trace back this difference between the behavior of the tunnel and density of states and conductivity to the fact that tunnel and density of states is a very tricky object. It's not gauge invariant if you think in terms of system at all. Yeah? It's a green function which is calculated at certain energy. Yeah? And when you calculate a certain energy, it means that you integrate over different times. And at the moment you take single particle green function at different times, it's not a gauge invariant object. And because of this, the effects related to small q are important. So for conductivity, this effect cannot contribute, and this is because due to gauge invariance, if you take q equal to 0 and have fluctuations at finite omega, You basically sort of shape the system uniformly, and this doesn't. This is something that can be just eliminated. This doesn't create any electric field or magnetic field. You just change the potential like this in time, but uniformly in space. But this effect does affect the Kalman density of states, so one should be sort of aware of this difference. Now, natural question, of course, if it's not gauge invariant, why do we speak about it? And I pointed that one can measure it, even though it's not gauge invariant. And the reason is that it's not gauge invariant only if I look at the system itself. So it will be gauge invariant, of course, if I include also my tip from which I tunnel. However, if I now fix a convenient gauge in which the green function in the tip it has some simple structure, and this is what is normally it's convenient way to calculate, and then this green function of t can it's just more or less a constant. What remains is the green function of my system, but already in certain gauge, and this is not gauge invariant object there. Good. Yeah, and now, so that was about renormalization effects. So what about dephasing effects? So dephasing effects are due to just inelastic scattering. There is a finite electron lifetime, and therefore all infrared sort of singular effects are cut off by this time. So in the quantum interference effects like weak localization, or this is called conductance fluctuations, or bone oscillation. So quantum coherent effect will be cut off by this time. So yeah, so this time scales as it's conventionally called tau phi. This lifetime, and it scales at a temperature to some power. The inverse lifetime scales, inverse dephasing time scales at temperature to some power, and this power p is a matter of calculation. And it's not quite trivial calculation for the following reasons. Naively, you could say, why don't we just calculate it by golden rule? Yeah, that's. But it turns out that when you just naively calculate it by golden rule, you encounter in low dimensions infrared divergences, and so one should take care about these infrared divergences. And more or less, what happens is that these infrared divergences are sort of cut off self-consistently by the time tau phi itself, but one can do it more accurately, and that was done in a famous paper by Militsky in 82, and there is a sort of simple way. I mean, they do a path integral calculation, but there is a very simple way to present their results on one slide, and it's the following. So this dephasing can be understood as just effect of Nyquist noise produced by the electron bus on one given electron, and according to the fluctuation dissipation theorem, just write this fluctuations of the fluctuating potential, imaginary part of the interaction propagator times this potential hyperbolic. And this is of course a classical formula, so it's valid only for frequencies below temperature. So but we will see that the integral will be determined by these frequencies, and so everything could be indeed use it.
Why is it classical and hence it has cotangent there?
Okay, no, okay, so
You say you want to look at classical limit.
I will, yeah. So we will go into the classical limit. So we will replace the cotangent by the corresponding behavior T over omega at low omega, but the whole method of calculation. So this formula is of course quantum, but the whole idea that we replace the interaction by this noise and study one electron in this noise is applicable only in this classical regime. So if you would naively do it in the opposite regime, you would get a a nonsense of finite dephasing at zero temperature due to quantum fluctuations, and this will be wrong. So we can use it only, this type of calculation only in the classical regime.
For you, you're using is it a short range screen interaction?
No, that's a screen. This will be. This is whatever an interaction is. It's a full interaction propagator. Of course, it should be screened if it's bare interaction. We don't have any imaginary part, and but whether it's short range or long range. So we need electron hole pairs, of course. Yeah. It's in any case the full interaction.
No, I guess I meant U0 inverse in the next line, in the definition of U. Is that cool? You take it Coulomb or in the denominator?
Yeah, okay. So here it's calculated for Coulomb, but we can do in principle this calculation. Yeah. So here it's calculated for Coulomb interaction, and for Coulomb interaction, U0 minus 1 can be just thrown away, and so the interaction becomes universal. It's just given by the polarization operator. Yeah, that's a property of Coulomb interaction. And okay, so now we plug in this here and get the integral for tau phi for the dephasing rate, which is due to these fluctuations, which goes as dq or dq squared, and the upper limit of integration is set by temperature, just because we cannot go with this calculation above temperature. But we see that in 2 dimensions or below 2 dimensions, it will be determined by logarithm. So in 2 dimensions, it will be logarithmic, and then the question what we put here. And the answer is that, yeah, that's an equivalent way of writing this in frequency space. And so we have this infrared divergence, and it turns out that one can show that when this tau phi is the one that is used for cutoff of the big localization, the result is cutoff self-consistent. A priori, it's not clear, and for example, for Aronoff-Bohm oscillation, that will not be correct even, but for big localization, you just should cut it off self-consistently. So you put here tau phi itself as a lower cutoff, or L phi corresponding with tau phi, and as a result, you get in 2 dimensions to the power 2/3 with fractional power. This is the result of the self-consistency. And in 2 dimensions, you get T, and out of the self-consistency, you get just logarithmic T over G, where G is a dimensionless conductance, and self-consistent also produces this log G out of this logarithmic equation.
But what's a good definition of tau phi? Like, what is that tau phi?
Yeah. So okay. So once again, so a priori, you would say tau phi is just inelastic time. And if the inelastic time would be convergent, so just the lifetime of electron, the inelastic lifetime of electron, then that would be it. Yeah. Then, however, in these low-dimensional situations, if you just calculate it naively, it diverges. It's infrared divergent, and therefore, which means, of course, for physical processes, there will be always some cutoff. However, it may depend also on what physical process you consider. And basically, the definition of tau phi is that, for example, is a tau that will cut off the logarithmic big localization. Let's call it tau phi. It's what plays. So if there will be a finite lifetime in a normal sense, that will be just this lifetime that will stay here. So now, essentially, that's a lifetime of electrons. However, it's one should take care about this infrared processes, and this regularization may depend on the phenomenon.
But I don't understand. What's a life? How do you define the fundamentality? Never mind. Okay, so there's this additional issue when it diverges, and so you have to define it self-consistently. But suppose it doesn't diverge.
Oh, well, it doesn't diverge. It's similar to the lifetime in, I don't know, in Fermi-Lickis theory. Yeah? You have
if I want to
lifetime.
calculate,
Huh?
if I want to calculate from first principle, I want to see some definition. Is it just imagining part?
Well, so once again, you want definition. Definition is what, for example, in 2D, the time that cuts off the logarithm in big localization. If you're happy with this definition, this is how we define tau phi. Now, once again, if there would be a finite lifetime, you just calculate it by, I don't know, by golden rule. How you calculate in Landau Fermi-Lickis, but just with diffusive best diffusive propagator. You calculate in the same way. So if it's finite, then it's just in elastic time it will cut off your.
I guess what I'm saying is that, so if I look at this single particle Green's function, it has an imaginary part.
Yes, yes.
But you can have an imaginary part just from disorder, and I don't. That's not really an elastic because
That's not an elastic. Yeah,
Right.
that's not it.
What's the fundamental way of distinguishing? I know if I can solve the theory exactly, then there'll be some cutoff in the weak localization corrections, and then I identify that. As
Yeah, you can define this. Okay, there are different ways to define this. So one question, so imagine, you can ask the following question. People deal with the calculation this way. Imagine you have your problem first without interaction. Then there are exact single particle states. And from this single particle states, the particle stays there. Yeah? Then you can ask a question, now you do interactions and low temperature. So there will be a finite lifetime in this state, and then you will get out of this state, of this exact single particle state.
Right.
Now you can calculate it. I mean, that's, and if you write it, it turns out, yeah, that will be more or less the same time, except that we should take care about this infrared regularization.
Right, it's defined as.
It's a lifetime. You can think about this as lifetime of exact states,
Single particles.
exact single particle states. Yeah, okay, now I understand your question.
As opposed to the tau that you see, that's a lifetime.
So the
for
tau-
getting out of a momentum eigenstates.
Exactly. Tau is a lifetime of momentum eigenstates,
Right.
and this is a lifetime of sort of exact single particle states.
Okay, that's conceptual, but how do you actually do it? Like, where did that integral come from? Like, you have an integral written down. Is that equal to some correlation function, or what?
Okay, so that's sort of basically one line calculation. So basically, you say you have your electrons, you subject your electrons to some random noise, yeah, and you ask what will be the decay time of your states due to this noise. Yeah, it's relatively easy to formalize it.
I get.
I mean, in the ultimate theory, it would be just the width of the peak of the quasi-particle.
I guess conceptually I understand it, but like you have a line there which says tau phi inverse equals to some integral.
Okay.
So tau phi inverse equals to then an integral. So what is that integral? Can it be written in more general terms, like, you know, like let's say, you know, in terms of Green's function, but can it be written in some?
I mean, so this is very much phenomenological calculation. You just put a noise. So I understand what you want. In terms of Green function, you should do the following. Yeah, there is a paper by Abrahams. So this again. So basically, you ask a question. You have your exact eigenstates. So you essentially calculate self-energy due to interaction. Self-energy of your exact eigenstate due to interaction. Yeah, that's a well-defined
Single particle.
equation. Yes. It's a single particle self-energy of exact eigenstates due to interaction.
Okay.
So basically, you draw the conventional diagram.
Okay, so it's right. So it's self-energy, but
So in a diagrammatic level, it's nothing. In a diagrammatic level, it's basically it's a usual diagram like this. But the only that now you should take care that these are exact eigenstates. And these are exact eigenstates. You should average over this order, and it means that there will be an impurity ladders here. And there will be impurity ladder, the corresponding impurity ladder here. So essentially, it amounts to calculating the for short range interaction, it amounts to calculating this object. Once you include impurity scattering, for Coulomb interaction, you should sum the whole sort of Coulomb RK type sequence with the corresponding polarization operator. That's what it is diagram. So it's, I think, very well posed question. It's just the lifetime of states of sort of disorder defined states due to interaction. Good. So what does one see in experiment? Yeah, one does see these power laws very reasonably. No, I lost my pointer. Yeah, so don't go into details. And so basically what's shown here are, I think, one-dimensional and two-dimensional systems, and the behavior of the dephasing rate that is extracted out of weak localization, because it's what cuts off the weak localization, and as explained before, that's the way to extract it. And you look at it as a function of temperature, and it shows the power laws, and the power laws are such that are expected to be seen. Okay, so I have still 10 minutes, so let me say a few words about what it does at transitions. Yeah. So at Anderson transitions, the interaction may renormalize the behavior in various ways and to various extents. So one can, yeah, and in general it does modify the critical behavior and does modify the renormalization group. And the corresponding theory was developed by Finkelstein in 1983, which was who included interaction with sigma model and then did renormalization group calculations. So depending on the symmetry class and on whether interaction is short range or long range, there are maybe very different types of interaction effects. So I try to sort of classify them in increasing importance. So there are situations when interaction is RG irrelevant at the transition, and it means a fixed point remains unchanged, and critical indices, those that are not related to interaction, also remain unchanged. Interaction still is important and called formally dangerously irrelevant from the point of RG, because it determines the dephasing rate, which means it determines the where to stop the transition, and there are, so the dephasing rate is something that would not exist without interaction, and for example, finite value of say conductivity at the quantum Hall effect at finite temperature at the transition point is only due to this finite dephasing rate. So one cannot discard interaction completely. However, for the RG equations, it's not important, and essentially one can calculate everything because fixed point, I mean everything, if one knows the non-interacting fixed point, one can calculate everything because everything is determined by the properties of the non-interacting fixed point. Yeah, so example of this is a case of broken spin rotation invariance and short-range interaction. For example, quantum Hall effect. Where let's say it's a due to magnetic field, forget about spin, and if interaction is short-range, if you would consider quantum Hall effect with short-range interaction, not with unipolar interaction, then the fixed point will be not affected by interaction. Now, the second case is that there are new fixed points and therefore new critical indices. However, the phase diagram remains qualitatively unchanged. So example of this is, for example, the same quantum Hall effect, or another more general system with broken spin rotation invariance with a Coulomb interaction. So if we take quantum Hall effect or Anderson transition in the same symmetry class, unitary class, say, with and without spin, yeah. It's in 3 dimensions, then we will see essentially the same qualitatively the same behavior. However, the fixed point will be different and critical indices will be different. So quantum Hall phase diagram with Coulomb interaction and without Coulomb interaction looks very much similar. However, fixed point changes, critical indices are expected to be changed. Yeah? And finally, there are situations when interaction is not only irrelevant but also leads to new phases, and this in particular happens when there is a preserved spin invariance, because in this case, as I just will explain in the next few minutes, the interaction, well, basically it already shows from what I showed you before, from this Aronoff correction, that interaction may change localizing behavior to so to say, anti-localizing and therefore, for example, may create a metallic phase in the case when there was no metal in the absence of interaction. So what does the dephasing do near an Anderson transition? It determines, yeah, as I said, it produces the finite length scales, the dephasing length that scales as a temperature to certain power, z, which is some dynamic exponent, and this length determines smearing of the transition. Yeah? So at finite temperature, the transition will, there will be not a transition, it will be smeared, and the way how it is smeared is determined by the dephasing length. So basically, this smearing is temperature to the power kappa, and this kappa is determined by this by this dephasing length yeah.
So with the incorporation of interactions, how does the new sigma model look?
Yeah, I will just, that's, so the answer is on the next slide. And I think I still have time to show a couple of slides and then we stop. Yeah. So very schematically, what the sigma model is. Yeah. So I don't want to show everything explicitly because it's long and but ideologically it's simple. It's just so first of all, Q matrices are now matrices. First of all, we should forget about supersymmetry. Yeah? There is no supersymmetry anymore because with interaction it's just not equal. So we should use replicas. Yeah. In addition, since we have now inelastic processes, the Q matrix becomes also a matrix in the space of frequencies. So so Q is now a matrix in replicas, and in addition in the space of Matsubara frequencies. And in addition, depending on symmetry class, there may be additional indices due to spin or due to necessity to include time reversal to incorporate gluons. But the main structure is a replica structure, this Matsubara structure. So it's now the structure of the action. So the first term is the same. It's a normal diffusive term, looks exactly the same. The second term is the term with frequency. So this epsilon is just a matrix which corresponds just to Matsubara frequency staying on the diagonal. It's the same as frequency before. The new thing is that this term is now renormalized. So there is a z staying there. So for non-interacting theory, I told you there is no renormalization. So here there is a renormalization, as normally in theories with sigma models we would also expect that there is a field renormalization, and with interaction it exists also there. That is one of important points that was understood and it's emphasized by Sasha Finkelstein that that's including this Z renormalization in the sigma model. Finally, the last three terms are interaction terms. So these terms are bilinear on Q, which is quite clear. So interaction is psi to the 4. And since Q is, I mean, in terms of fermionic electronic fields, and since Q is something like density, is psi bigger more or less, so it's clear that interaction should be QQ times some matrix. So there are three different matrices staying there. I did not write them explicitly, but just to explain what. So physically they correspond to three different channels of interaction. So you may have interaction in the particle hole channel when Q and omega that are going through the small momentum at small frequencies are in the particle hole channel, so the arrows are in the opposite direction, like in diffusion. So this will be gamma S, gamma, I don't know the S and T, S, or S sigma, yeah, S and T. Gamma S, and there is also gamma T, so this corresponds to singlet and triplet channels. If you have a spin, then you should triplet, and then there is a Cooper channel interaction. Which everybody knows what Cooper channel is. Like in without interaction, we had a diffusion and Cooperon, quite similar to this now. We should distinguish between different channels. Yeah. So let me show one more slide, because at least I think if I show this slide, then I know at least I show the basic things, and then we can discuss. This is a renormalization. These are renormalization group equations for this theory, which are shown for weak interaction. They are all shown in linear order interaction strengths. One can do better, but in this way they're very much transparent. So the parameters, the couplings that flow are T, which is a resistance, it's inverse conductance. So T is these three gammas, and gammas are interaction strengths divided by C. Oh, yeah, that's here. So gamma capital divided by C is gamma small, so those are interaction strengths. And finally, the last equation is equation for C. And so this is shown for short-range interaction. For Coulomb interaction, one should replace gamma S by -1 and remove the equation for gamma S. And this is RG that was done by Finkelstein, so now this is for short range, which is includes also Coulomb case as a leading case. So now let's look at the equation, because they contain, so what is the physics they contain? Yeah. So first of all, yeah, I think I written here. But, yeah. So yeah, that's the least of what it is. So first of all, there is a weak localization term. Yeah, this is T squared. Yeah, this is a disorder renormalizes itself. Yeah, so T is disorder, and it's orthogonal class. There is a localization. The resistance wants to become larger when we go to the larger systems. Second, there is a second. Yeah, I'm sure I wrong. Yeah, there is this term. Yeah, so this term is a renormalization of disorder of resistivity by interaction. And this is the physics, around physics, and the sign of this. So yeah, so the definition of this gamma S and gamma T is such so. So gamma S should be localizing. So gamma S is negative, and gamma T is positive. Yeah, that's pretty simple definitions. So gamma S is localizing, and gamma T. This corresponds to this hard trick and exchange in the previous slides. So gamma S is localizing, gamma T, the triplet, is anti-localizing. Yeah? So when gamma. So this is actually a Aronoff type effect, which may lead to sort of anti-localization, increase of conductivity due to interaction. Then there is a renormalization of interaction due to disorder. You see the channels, interaction channels mix, and I renormalize it due to disorder. And the physics of this is in fact related to multifractality. So the fact, in particular, they will in general increase, and the fact that they will increase in general situation means that interaction is relevant. The short-range interaction is relevant, and the fact that interaction becomes larger, it becomes matrix element of fermionic wave functions increase, and that's, as we know, exactly the multifractality. There is one case when interaction will not increase but decrease, and this is when there is only gamma S channel, only singlet channel. Then the only term which remains is this one, and it is negative, so here the interaction will decrease, and that's the case that I mentioned when interaction is RG irrelevant, like quantum Hall is short-range interaction. So quantum Hall is short-range interaction, only keep gamma S, so this will be, so then interaction will sort of vanish on the origin. Okay, so this term is the only nonlinear term that I included here is the Cooper instability. That's, and finally, there is a renormalization of the factor Z, and it only exists due to interaction. But without interaction, it's zero, so Z remains unity as it is in non-trivial Z. However, with interaction, the Z flows, and it leads to non-trivial dynamical scaling. So the dynamical scaling exponent was trivial at simple without interaction, but it becomes non-trivial with interaction. So yeah, now depending, so as you see, this depending on the situation where we are, these equations can be analyzed, or in fact there are more general equations which are also include non-linearities in interaction, but the structure is similar and the physics is already understood here, and depending on what situation is, one can analyze this equation, and one famous result is, so let me go through to just one, but not to this one, these formulas. So this is what was done originally by Finkelstein and more recently generalized by Finkelstein in Toulouse. So these are two equations for the case when there is a triplet interaction, and so therefore there is a correction to resistivity which is anti-localizing, and there are just two equations. So this gamma, this is a Coulomb case, gamma s is -1, and this gamma 2 is gamma t from the previous slide. And analyzing these two equations, they obtained this plot, this so this is the resistivity and this is the interaction, and there is a flow to a sort of metallic fixed point, zero resistivity, large interaction, and to insulated fixed point, infinite resistivity. Zero interaction, and between there is a metal insulator transition, so one should be somewhat careful here because in fact this theory has some instability, ferromagnetic type instability. However, it turns out that when the number of flavors of electrons of Velis is large, this instability happens at exponentially small temperature, and so it becomes academic, and already for 2 Velis, which is characteristic for the silicon samples where metal insulator transition in 2D is observed, this temperature is extremely low, and so if one forgets this extremely low temperature regime, then this theory yields a transition in 2 dimension in the symmetry class where without interaction everything was localized, this was correspondence or orthogonal symmetry class, and there is a sort of belief by large, at least not only by the authors, but I think a large part of the community that this explains the observed metal insulator transition by Kravchenko. So, but the question is whether some parameters of experiments are indeed such that this theory is applicable, and these parameters are those that say scattering between these Velis, and which should be sufficient for this to be applicable, and so there is some still debate on this, but at least on the level of theory, I think that's a nice way how interaction produce some physics view